Hello, we have here another example of linear programming, specifically under minimization. So let me read the situation. Two dietary drinks are used to supply protein and carbohydrates. The first drink costs $4 per liter, and the second drink costs $2 per liter. The first drink provides 1 unit of protein and 3 units of carbohydrates in each liter. The second drink supplies 2 units of protein and 2 units of carbohydrates in each liter. An athlete requires 3 units of protein and 3 units of carbohydrates. Find the amount of each drink that the athlete should consume to minimize the cost and can still meet the minimum dietary requirements. So given the situation, we need to identify then the decision variables. So on the first sentence, it is said that 2 dietary drinks are used to supply protein and carbohydrates. So we could consider the first drink and the second drink as our decision variable. So let X be the number of the first drink and let Y be the number of our second drink. Next one is we identify the objective function. Okay, the first drink costs $4 per liter. Okay, so 4, that would be $4. So the first drink is, we will be using X since we have already declared it as in our decision variable. Let the X will be our first drink plus the second drink will cost $2, so that would be 2Y. And then since we are dealing or we are going to find for the minimum cost, so that would be minimum cost is equal to 4x plus 2y. We proceed then with the different constraints. So the first drink provides 1 unit of protein and 3 carbohydrates, while the second drink supplies 2 units of protein and 2 units of carbohydrates in each liter. Or to answer it correctly, we may use a table. Okay, so we have X, that would be our first drink, and our Y will be the second drink. And then we have here protein and carbohydrates, or that is our carbs. First drink provides 1 unit of protein, so we could put here 1, and carbohydrates, that would be 3. And then the second drink will supply 2 units of protein and then 2 units of carbohydrates. Okay, and then for this sentence, an athlete requires 3 units of protein and 5 units of carbohydrates. So that is the minimum requirement that an athlete should take within a day. So we will be using, so that would be 3, and then this will be 5. To show that in an equation, we will just simply use the 1x plus 2y is greater than or equal to 3. So that would be under the protein. And 3x plus 2y should be greater than or equal to 5. That is under the carbs. And our non-negativity constraints, that is our x and y, should always be greater than 0. Those are our constraints. So given our constraints, we can already compute for the graphical solution. We'll treat first the first constraint. So the first constraint is x plus 2y is greater than or equal to 3. To get the value of x and y, we are going to treat this as an equation. So x there will be our 3 and our 2y is equal to 3. We divide this by 2, so we would be able to cancel 2. So 3 divided by 2, that would be y equals 1.5. So if we're going to graph that one, our x is 3 here, 1.5, and 3 is here. So we are going to connect that one. Okay, so we have there the graph. Should I say x plus 2y is greater than 3? Our next one, we are going to compute for the x and y using the second constraint. So our second constraint is 3x plus 2y is greater than or equal to 5. Again, we are going to treat this as an equation to get the value of x and y. So 3x is equal to 5. We divide both sides by 3. And then we cancel 3. So x is 1.6666, or x is equal to 1.67. And then the second one, 2y is equal to 5. We divide both sides by 2. And then we cancel 2. The value of our y is then 2.5. We are then going to plot it in our graph. So maybe around 1.67 is around here. Okay. And then our y is around probably here. That would be 2.5. And then we connect this line. Okay. So since we are dealing with minimization, the shaded part in our graph is above. So this part is our shaded part. So any values that would fall within this part of the graph is okay, since we are dealing with minimization. The only thing that we are looking for is the number of units per drink to minimize the cost, but at the same time, the athlete would be able to meet the protein and carbohydrates requirement. Since we have already computed for the different values, so 1 point is here, that would be 3 and 0, our point. For this point, that would be 0 and 2.5. Next one is we are going to look for this point, our optimal point. So to get the value of our optimal point, we will be using our two constraints. Our constraints, x plus 2y equals 3 and 3x plus 2y equals 5. Using these two constraints, we need to get it's either the value of x and y first to compute for the optimal point here in our graph. So for this example, it would be easy if we cancel 2y since they do have the same numerical value. So I'm going to multiply the first equation with negative 1. So it would be easier for us to cancel negative 2y and positive 2y. So for this one, we are going to multiply the whole equation with negative 1. So negative 1 times x, that is negative 1x. Negative 1 times 2, that would be negative 2y, equals negative 1 and 3, that would be negative 3. The second constraints, we will just simply going to copy. 3x plus 2y equals 5. So in this situation, it is already easier for us to get the value of x since we could already cancel negative 2x and positive 2y. So negative 1x and minus 3x, that would be 2x is equal to 5 minus 3, that would be 2. So again, to get the value of x, we're going to divide both sides by 2. And then we cancel 2. So x is 1. We have already the value of x, which is 1, or we are going to substitute 1 in any of these two constraints. So I'll be using the first one. So x, that would be 1 plus 2y equals 3. So 2y and then 3. The 1 here, I will be going to transpose it to the other side. So we will be changing the sign. That would be negative 1. And then 2y is equal to 3 minus 1. That would be 2. Again, divide both sides by 2 to get the value of y. So the value of our y is then 1. So at this point, our optimal point here, that would be 1 and 1. We are then going to use these 3 points to substitute using our objective function as to which of those 3 points we are going to get the minimum cost that would be used by the athlete. If we could recall, our objective function is minimum cost is equal to 4x plus 2y. And then our points, we have 0 and 2.5. The next one is 1 and 1. And 3 and 0. Using the formula above, we are then going to substitute using this values. So 4 times x, that would be 0, plus 2 times 2.5, okay, that would be 0, plus 2 times 2.5, that would be 5. So for this point, our value would be 5. Let me proceed with 1 and 1. 4 times 1 plus 2 times 1, that would be 4 plus 2, that would be 6. And then for this point, that would be 4 times 3 plus 2 times 0. Okay, that would be 12 plus 0, or simply 12. So at this point, the minimum cost would be at point 0 and 2.5, or our computed result was 5. So to interpret, to get for the minimum cost of the athlete's drink, and at the same time the athlete would be able to still get its minimum requirements for the proteins and carbohydrates. So the athlete will not drink the first drink, but to still get the minimum requirements, the athlete will drink 2.5 of drink 2 a day. So at this point, even though the athlete will not drink the first drink, he or she will still be able to meet the minimum requirements for the protein and carbohydrates if he or she drink 2.5 of the second drink a day. That answers our word problem in linear regression, specifically the minimization. So if you have questions, feel free to comment down below. So that's it. I hope you understood linear programming, including the graphical solutions. Thank you.